Hi everyone, welcome to lesson 2.6 where we're going to continue graphing quadratic functions. So let's take a look at our document. What we've previously been working on is a graphing quadratics in standard form. And standard form is y equals ax squared plus bx plus c. And knowing what a, b, and c are helps us determine certain characteristics of the quadratic, and so it helps us graph. Now, in this lesson, we're going to focus on another form, and it's called vertex form. And from the name, hopefully you can determine that this form gives us the vertex right away. So in standard form, we had to use the equation x equals negative b over 2a, and then we had to sub that into the function so we could get y, and that would be our vertex. Well, in vertex form, which is y equals a times x minus h squared plus k, the h and the k are actually the vertex. So helpful when we want to find the vertex quickly if the function is in vertex form. All right, so let's take a look at the parent function y equals x squared and the graph. We know all of these characteristics already, but the vertex is at 0, 0. And let me pick another point, maybe here. This is 2, 4. And I'll plot, obviously, the other point, too. So negative 2, 4. So some key points from the parent function. Now let's go ahead and take a look at the graph of y equals, in bracket, x minus 2 squared. Let's just say I use a table of values, or I just use Desmos. Let's take a look at the characteristics here. Now the vertex has moved over, and we are at a vertex of 2, 0, looks like. And then here, looks like my point 2, 4 has become 4, 2. Sorry, 4, 4. And then the other point went from 2, 4 to 0, 4. So if you compare them, what has changed? Well, it looks like the x values have changed. So really what's happened here is that the graph y equals bracket x minus 2 squared is shifted to the right 2 units. And that's compared to the original function, or the parent function, y equals x squared. My third graph here, here's a graph of y equals x plus 2 this time. So let's zoom in here and we'll take a look at, here's the vertex now, and this vertex looks like it is at negative 2, 0. Plotting similar points, I now have, this is negative 4, 4. And over here, we have 0, 4. So what's the difference with this graph and the parent function? Well, this graph, y equals x plus 2 squared, is shifted to the left this time, 2 units, as compared to the parent function y equals x squared. So here I want to be able to state the axes of symmetry, let's go back to our graphs and actually draw them in. So remember the axes of symmetry, they go right through the vertex of each of the graphs. So here, for the parent function, going right through the vertex gives me an axis of symmetry of x equals 0. For the second function, going straight through the vertex gives me an axis of symmetry here of x equals 2. And then in our third graph, we get an axis of symmetry going through this vertex is going to be x equals -2. Let's go ahead and plug that in to the document where x equals 0, x equals 2, and x equals -2. Those are the three axes of symmetry that correspond to each of those three graphs. So let's summarize some of the things we've just investigated. So subtracting a value of h inside the brackets causes the graph to shift to the right. Adding a value of h in the brackets causes the graph to shift to the left. The value of h in vertex form of a quadratic coincides with the axis of symmetry. All right. So take a look at graphing y equals a times x minus h squared. So here, remember, a always causes a stretch or a compression or a reflection. So let's compare the parent function, y equals x squared, with a function in vertex form that is y equals 1/2 times bracket x minus 4 squared. So we can start by graphing the axis of symmetry, and because the h is 4, the axis of symmetry is x equals 4. If we want to find the vertex, we have to plug in h into the function. So it would look like 1/2 times 4 minus 4 squared. And that just gives me a value of y equals 0. So then we would plot our vertex at 4, 0. We only need a couple more points in order to graph parabola. So we could find 2 more points on the graph, any 2, and then we can evaluate those and maybe use symmetry to find the others. So for here, let's choose x equals 0 and x equals 2. They seem to be easy to work with. So again, we're trying to find a couple more points on the graph. So we have the axis of symmetry and we have the vertex. Now we need to find 2 more points. So here I'm going to do the work. Y equals 1/2 0 minus 4 squared. Y equals 1/2 times 16. So y equals 8. So one point that I can graph is 0, 8. Then I wanted to use x equals 2, so I'll plug that into the function, 1/2 times 2 minus 4 squared, y equals 1/2 times 4, and y equals 2. So another point I can graph is 2, 2. So let's go to a graph and let's plot those points. So we said that the axis of symmetry is x equals 4. So here's 4, and I'm just going to sketch that down here. That's x equals 4. Then the vertex we determined was 4, 0. So I'm going to plot here. That's my vertex. Then I found two other points on the graph. One was 0, 8. And then the other one was 2, 2. Using symmetry, I'm going to plot the points that are a mirror image of these. Oops, missed this one. And then I can graph, oops. Graph my parabola. And there you go. All right, let's take a look at another example. Okay, so now we know what h does to our function, and it shifts it left or right. Now let's take a look at adding k. So adding k in vertex form, that is going to change our graph vertically. So for now, let's go back to using a table of values. And I know it takes a little longer. So here we go. Y equals 2 times 2 minus 4 squared plus 2. Y equals 8 plus 2. Y equals 10. Put 10 here. And then y equals 3 minus 4 squared. Oh, forgot to times by 2. Plus 2. So y is equal to 3 minus 4, 1 squared, 2 plus 2. So y equals 4 here. And then we have y equals 2 times 4 minus 4 squared plus 2. That gives me y equals 2. And then y equals 2 times 5 minus 4 squared plus 2. Y equals 4. And then the very last one, y equals 2 times 6 minus 4 squared plus 2. And that's going to simplify to 10. So I'll go ahead and plot these points. And I have 210. So 210. It's way up here. I have 3, 4. I have 4, 2. 5, 4. And then 6, 10. So I'll draw in my parabola there. All right, so the vertex of the graph, we can draw that in. Again, it goes straight through the vertex, which looks like it is right here. The vertex looks like it is at 4, 2. Axis of symmetry is x equals 4. So I want you to pay close attention to the vertex here. Which was 4, 2. And the h value and the k value in the function. And you can see that they match up. So H and K in a function in vertex form corresponds to the vertex of the parabola. So subtracting a value of K causes the graph to shift down. Adding a value of K causes the parent function to shift up. And the value of K coincides with the Y value of the vertex. So again, let's review the domain and range. Remember, domain for all quadratic functions, they are all real numbers. Now range is all the Y values, and it depends on the value of A. And if you recall from before, if A is less than 0, then the range is Y greater than or equal to the Y coordinate of the vertex. And if A is greater than 0, then Y is less than or equal to the Y coordinate of the vertex. Reviewing real quick, maximum and minimum, again, depends on that A value. And if A is positive, the parabola opens up and the vertex would be a minimum. And if A is less than 0, the parabola opens down and the vertex would be considered a maximum. And we took a look at that in the last lesson. So let's move on here. The vertex of the graph here is 0, 0, and it opens down. So 0 is a maximum here. So let's take a look at example 1, where we're asked to find the vertex, the axis of symmetry, determine if there's a maximum or minimum, and the domain and the range given the function in vertex form. So let's start by identifying the parts of the function. In this function, we have an A that is equal to 3. We have an H inside the brackets that's equal to -1. Remember, it's always opposite what's inside the bracket. And we don't seem to have anything out here outside the bracket, so our K here is 0. So our vertex would then be -1, 0. The axis of symmetry is equal to the x component of my vertex, so that is y equals -1. In this situation, I have an A that is greater than 0, so I have a minimum. And the domain of all quadratics is x is an element of all real numbers. And the range, because I have a minimum, is y greater than or equal to the y component of the vertex, in this case, 0. Taking a look at another example. Here, we have A is equal to 1/4. Our H is equal to 6. Again, always opposite what's inside the bracket. On the outside of the bracket, we don't seem to have a K, so our K is 0. Writing out the vertex, it'll be 6, 0. The axis of symmetry is the x component of the vertex, so x equals 6. A is greater than 0, so we still have a minimum. The domain of a quadratic function is that x is an element of all real numbers. The range coincides with the y value of the vertex. We have a minimum, so y is greater than or equal to 0. The third example is similar, so I'm going to let you work on that one. But we're going to take a look at example 2, finding the vertex, axis of symmetry, maximum, minimum, domain, and range. And this time the vertex form of this quadratic looks a little different. Here we have an A that is equal to -6. We have an H that is equal to -4. Again, opposite sign to what's inside the brackets. And we have a K that's equal to -3. So our vertex here for this function is -4, -3. Our axis of symmetry coincides with the x component of the vertex, so it is x equals -4. Our A is less than 0, so we have a maximum, and that maximum value is the y component of the vertex. The domain of a quadratic is all x values are an element of real numbers, and the range is y equals, less than or equal to, in this case, -3. We'll do one more together. For B, A equals 3, H equals 3, and K equals 6. So the vertex is 3, 6. The axis of symmetry again coincides with the x component of the vertex, so that is x equals 3. A is greater than 0, so we have a minimum. The domain of a quadratic function is that x is an element of all real numbers, and y, or the range, is y less than or equal to 6, which is the y component of the vertex. I'll leave you with the third one to practice. Now, let's see if we can match up the function with its graph. So I have 3 functions, 1, 2, 3, 4, and then I have 4 graphs, A, B, C, and D. And I want you to be able to match up the graph with the function. So for number 1, the first thing we can take a look at is I have a negative A. If it's a negative A, I know my parabola has to open down. Next, I know the H and I know the K, and that gives me the vertex. So in this case, it is -1, -3. So if I look at my graphs, I'm looking for a parabola that opens down and a vertex of -1, -3. And in this case, that is C. So number 1 is C. Similarly, for number 2, again, we have a negative value for A. So we have a parabola that opens down, and the vertex here is 1, 3. So let's go down to our choices. Again, we're looking at something that is opening down and has a vertex of 1, 3, and it looks like it's this one here, A. So we're left with the other 2. And we have 3 and 4 that are both positive A's, so which means they're opening up. This one is A. And then we're looking for vertex. So for 3, we're looking for a vertex that is 1, 3. And it looks like here is 1, 3. So that one is it. So 3 is D, and then number 4 is B. Next couple of examples, again, we don't want to just be able to graph them, but we want to be able to describe the changes of the functions compared to the parent function. So if I take a look at A, I have an H and I have a K. Again, H causes shifts left to right and K causes shifts up and down. So in this particular case, we have a graph that is shifted to the right, again, kind of opposite the sign that's in the brackets, 2 units, and up 4 units. If we take a look at B, we have this negative sign out here. So this graph is flipped upside down and shifted left 4 units. Remember, opposite what's in the bracket. And up 2 units. Good. For C, we have a negative 1/3. So it is flipped, but then it's going to be vertically compressed. So this is flipped upside down. And compressed, let's say vertically compressed, by a factor of 1/3, and then shifted left 3 units and down 2 units. And we'll practice this last one where we have coefficient of 4. So this is vertically stretched. It's going to get skinnier by a factor of 4, then shifted to the right 1 unit and down 5 units. Good. So hopefully you're starting to get a hang of the H values and their shift horizontally, and the K values and how they shift the graph up and down. And don't forget about that A value, the coefficient in front will tell you whether it's a parabola that's flipped upside down or whether it's vertically compressed or vertically stretched. Now, let's take a look at an application. So we want to be able to use quadratics to start modeling some situations in the real world. So let's take a look at this example here. So water fountains are usually designed to give a specific visual effect. And for example, the water fountain shown in the picture has a bunch of different streams and they're all shaped like parabolas. So we're going to write and graph a quadratic function that models the path of the stream of water with a maximum height of 5 feet, represented by a vertex of 3, 5, and landing on a spotlight that is 6 feet from the water jet, represented by 6, 0. So let's start by understanding the problem. So streams of water have a shape like a parabola. Therefore, the shape has to fit some kind of quadratic function. Now, at this point, we know quadratic functions in standard form and in vertex form. But here, we were given a vertex of 3, 5. So we're going to use vertex form. Now, vertex form is y equals a x minus h squared plus k. The vertex is given to be 3, 5, and that's from the word problem. Let's go ahead and plug these values into the vertex form of the quadratic. Y equals a, x, instead of h, we'll use 3, instead of k, we'll use 5. Now, what we don't know in this form is we don't know the a value. So in terms of finding a, we have to come up with some other point to help us. And if we go back to the question, we were given a different point, 6, 0. So 6, 0 is really giving us an x and a y value that we can use. If we have an h value, a k value, an x and a y value, then we can plug those into the equation and find a. So let's do that. Instead of y, I'm going to write 0. I still don't know what a is. We're trying to find that. Instead of x, I'm going to write 6. And my h value was 3, and my k value was 5. So now if you take a look at this equation right here, the only missing variable is the a. So let's go ahead and solve. 0 equals 6 minus 3 is 3 squared. So I'll have 9a plus 5. I'll move that 5 over to the left side, and it will become negative 5 is equal to 9a. And if I divide through by 9, I'll have a is equal to negative 5 over 9. And so finally, we can state what our function is that matches the shape of this water fountain. And it will be y equals, the a is negative 5 over 9, x minus the h is 3 squared, and the k is 5. So we have modeled the shape of the water fountain in a quadratic function. So that was a lot for today. I know there's probably a lot going on, but Let me know if you have any questions. Take a look at the homework. Please reach out.